Okay, so I'm welcome Yvan Capowiez today to talk about a subject that is very close to my heart, earthworms. I personally invited Yvan because I think the research that they've been doing over in France is absolutely fantastic, and it's changing the way we think about our earthworms. So Yvan, over to you.
Thank you. And thank you for the invitation. And today I will speak about functional groups of earthworms, and we can consider that it's something like an holy grail in earthworms ecology. Okay, and of course the starting point of my talk is about ecological categories. I assume you all know the epigeic, anecic, and endogeic earthworms. These categories were defined by Marcel Boucher in the 17th. And he defined as well something that we all forgot, additional categories such as epianecic, epiendogeic, endoanecic, and intermediate categories. He used only morphological characters, such as length, color, etc. And what is very important to understand is that Boucher wanted to understand why a species was present in one site, but he never assumed to describe what earthworms will do in the soil. Okay, it was a success story because for sure Boucher is one of the most cited French researchers in the world now. And but Marcel was not the only one to try to categorize earthworms. Lee in New Zealand did the same independently. And Lee defined as well three categories that were a bit different. It was litter species, topsoil species, and subsoil species. And it means that he studied where they live and what they feed on. A big difference with Marcel Boucher is that he used the burrows as a criteria. He compared permanent burrow system to extensive burrow system. It means, do the worms reuse the burrows or not? After a while, people mix the two classification. Marcel won and Lee won, and everybody was thinking that ecological categories did different burrow system in the soil. Okay, so at this stage, perhaps everything is okay. We've got ecological categories, and thanks to Lee, we can understand what they do in the soil. However, it was not that simple. For example, Lee already note that there was huge difference between the two classification. I won't enter into details here, but for example, the black criteria means that they are not the same between Boucher and Lee. You can see here that there is at least 4 criteria or 9 that were different. Okay. But there is something like a mini revolution after in this century, because there is a lot of observation of earthworms' behavior that did not fit the pictures. It was especially true for burrowing behavior. And we observe as well failure in meta-analysis, for example, regarding cast characteristics. It was very difficult to understand what happens. For example, some people note that you can observe endogeic species very deep in the soil, something not expected, etc. And we think that part of the problem comes from the fact that Boucher only wrote in French, and I say that something was lost in translation. Okay. Something important to note is that Boucher himself, from the beginning, states explicitly that endogeic, epigeic, and anecic were not separated groups. You can find this ternary plot in his publication, and he explains that every species can find a different location in the ternary plot, meaning that you can observe very different situation for every species. And just here, I note that, for example, Caliginosa, called by Boucher Nicodrilus caliginosus caliginosus, he was not so endogeic, for example. He's perhaps more close to the epigeic pole. Something a bit strange, but let's see what happens. And I have to say that Boucher himself presents some problems in his book. And for example, he changed his mind about the criteria he used to define anecic, endogeic, and epigeic. He used 11 criteria first, and then later 15. It was never explained why, and it's like that. But worse, it did not provide assignation rule. It means that nobody can say these new worms can be an anecic because we knew how he did that. In his book, he never defines the intermediate categories, and it's a bit strange. And there is something like 40 species that were never assigned in his book. And something funny for English people is that he did not remember how the ternary plot I presented you previously was done. He just tells us, oh, I remember it was done by an English researcher, but I don't know where he did and why. Something strange. It means that at this stage, we think that we should revisit the data of Marcel Boucher, and it was done in this publication. And the idea is very simple. We've got everything in the book of Marcel Boucher. Okay, he defines the species with morphological criteria. He assigns most of the species. It means that it's quite easy to ask the computer to explain to us how Marcel Boucher did. This is something like a reverse engineering process. And when we do that, I don't want to enter too much into the method, okay? You can, the computer responds that the most important criteria for the classification were, it was not a big surprise, skin coloration, length of the earthworms, pigmentation, and weight of the earthworms. And if you are used to earthworms, and if you sample them in the field, this is something we all use in the field to try to assign an earthworms we see in the field to ecological categories. Is it a big, large, dark earthworms or not? Something like that. Okay, using these techniques, it was quite easy for us to locate all the species Boucher described on a new triangle, as you can see here. Of course, I cannot comment every species here, but I want to say that, as you can see, there is species everywhere in the ternary plot, of course. And I will choose only one example because I think it's an important example, is the Allolobophora chlorotica, the green morph. You got a lot in the UK. And for example, you find it in the center of the ternary plot. It means it's 41% epigeic, 41% anecic, and 48% endogeic. And it's quite funny because if you go back to the book of Marcel Boucher indeed explained that this worm was intermediate. He never said this worm was endogeic. But if you look at what the people say, and I did it myself, everybody thinks this worm is endogeic. It means that even what Boucher told us in the 70s was not very keep in mind. And then, as a second step, we decide to write an opinion paper to really claim that ecological categories of Marcel Boucher are not functional groups. And why what are the arguments for that? The first argument is quite simple. Ecological categories were not defined to be functional. Okay, I already explained it to you, but the definition of the ecological categories were found in a chapter of the Marcel Boucher book called Chorology. It means that the main was to understand why a species was present in a forest, why a species was present in a wetland, but not to explain to the reader what earthworms will do in the soil. The second argument is that the relationship between these categories and soil function were never tested so far. And of course, as explained before, there were a lot of divergent observations regarding earthworms' burrowing behavior or casting behavior. And you can, if you read publication on earthworms ecology, of course, there is another holy grail. The grail is to relate earthworm species to soil functions and then ecosystem services. And you can find such example here, found in a paper. And it's a bit shocking because, for example, the author says that epigeic, anecic, and endogeic earthworms are functional groups. Okay, I disagree. And worse, they explain to us that Lumbricus castaneus, the very small red earthworms, here in the table is written as endogeic, whereas for Marcel Boucher, this is the most epigeic worm possible. It means that this is full of mistake, okay? And even in very good scientific journals like Science, you can find such a figure where they want to describe the categories, of course, epigeic, anecic, endogeic. And for endogeic, first of all, they choose Allolobophora chlorotica, a green one, as you can see on the figure. And I remember you that it's not an endogeic worm, it's an intermediate earthworm. And then if you look at what the author do on the figure, you can see it burrows deeper than the anecic earthworms here, Lumbricus terrestris. It's something incredible because Lumbricus terrestris can burrows as deep as 1 or 2 meters. And of course, if you know a bit, earthworms Allolobophora chlorotica is only found in the 10 or 21st centimeters, every time very close to the grassroots. It means that everything is false. So our conclusion is that there is a big mess. Okay, everybody wants to use ecological categories, but it's not always on purpose. I'll show you. And most of the people ignore the ternary plot of Marcel Boucher himself. Worse, people assume that these categories are indeed functional groups, but something Boucher never said or assumed. Okay, and then another problem that is not limited to Europe is that these categories are now used worldwide, whereas they were defined only for Lumbricidae earthworms. It means earthworms we can find in Europe only. So one of my most important conclusions is that for a beginner, either a citizen or a researcher, there is no way, no tool to understand accurately the concept behind the categories. So we have to do something. So the main question is now how to define functional groups for earthworms. And our idea is as well very simple, is we have to follow what earthworms are doing in the soil. And what they are doing is, above all, is physical influence. And this physical influence are, they make burrows, of course, they cast either at the surface or in the soil, and they eat and bury organic matter, okay? And this is all the different facets of something called bioturbation. So if we want to have functional groups, we need to study bioturbation. Another point important is that the number of species is not so high. It's quite limited in the UK, but in France there is a bit more than 100 species, and a lot of them are very rare. So it's not impossible to study earthworms behavior under lab conditions. And what we did is, it's a very simple protocol. We use repex soil cores, and we place only one earthworms in every core. We let him do what he wants to do for 1 month, and then we did that for 50 species in France, and with a very large variety of worms. As you can see, the largest one at that time was Sclerotheca chicharia, something like 50 grams. And the teeny one, not the most teeny, but one of the most teeny worms was Aporectodea cupulifera. Okay, and what is necessary now is to study burrowing behavior, casting behavior, litter consumption, and of course, what the worms is as well doing below ground. It means making cast, for example, and we call that bioturbated area to separate surface cast from below ground cast. Okay, as you of course know, soil is an opaque matter, so we need to use something special. This is the X-ray tomography to see through the soil, and we simply use a medical scanner. We take our soil core after 1 month, put it in the scanner, and the scanner will provide you sets of images where the density is described. If there is white part on the image, it means it's very dense. If it's completely black, it means this is void. And of course, void is what the earthworms did in the soil, and you can have 3D reconstruction of the burrow system of the worm. But if you look at the image you get after medical scanning, you've got burrows, porosity, but not only porosities. If you have a look at the image here, you can see pale gray zones. This means this is where the earthworms cast or influence the soil by pushing it along the burrow, for example. And this is what we will call bioturbation. It means that using the medical scanner, you have got porosity, burrow system, and what the worms did as casting below ground. And for the other method, it's quite simple. You can measure the quantity of casts, the deposit by the worms at the soil surface, and the quantity of litter that disappear after 1 month. It means you've got different parameters to follow what earthworm is doing. In this jar, I wanted to show you the great diversity of burrow system we got after 1 month. Of course, it is only examples. And what is important to note is that, for example, there is very, very intensive burrow system. Here, it's made by Sclerotheca earthworms, for example, Sclerotheca gigas rhodana and Sclerotheca shisharia. As you can see, the worms was burrowing a lot, really. And on the other side, you can find lazy worms only burrowing close to the soil surface, such as Lumbricus castaneus, or something a bit less lazy, but still, Lumbricus terrestris is not burrowing extensively in the soil. But perhaps the largest surprise for us was earthworms that only burrow deep in the soil. The example is here. It's Vinisia poppy, as you can see in the middle of the figure down. These worms only burrow very deep, and so did, but it's less marked, Aporectodia icterica. Okay? So, of course, we got plenty of data. We got 50 species. We've got a lot of different burrow systems. We know exactly what the earthworms eat, or where it casts, below ground or not. And you've got a big matrix. And if you want to analyze that, the best tool is principal component analysis. I don't want to enter into details. Methods are not very important here, but what you have to understand is that it's a projection of all the data on a plane so that our brain can read the data. And here you can see that there is a first horizontal axis that separates the quantity of litter consumed, and it's opposed to bioturbation or burrow volumes. It means you've got on the first axis earthworms that eat a lot at the soil surface or earthworms that are burrowing a lot. The second axis here, the vertical axis, oppose surface cast, meaning earthworms, once again very active at the soil surface, to burrow system with an important barycenter, meaning very deep burrow system. Okay, these two axes are quite meaningful if you think about what an earthworm will do in the soil, depending on is it active at the soil surface or, on the contrary, is it burrowing very deep. Okay, on the right part you can see all the species. Of course, there is some variability, but the ellipses are not so big. Species are all a bit separated. Once again, I don't want to discuss about methods, but we use Kamin's method to separate different groups in this space, of course. And the best algorithm give 6 groups, as you can see here. And now our work is to understand what are these 6 groups, okay? I will try to explain. For example, the group on the left is made of very large and very dark earthworms. This is, for example, all the Sclerotheca species. Okay, these are only Mediterranean species. You won't find them in the UK. And Ormogaster species, this is the same. But there is with them, you can find other large brown earthworms. The second group I want to describe here is a red one. This is where you will find all the Lumbricus means red large worms, and some brown but medium-sized earthworms. For the blue group, it's mostly, but not all of them, epigeic species. And of course, there is an intermediate group in the middle of the figure. It's not easy to characterize these worms. It means this is a continuous world. We cannot separate all of them. We have to accept that there is an intermediate group. It's a soft blue here. The two last groups are the black one and the green one are, well, I would say it's something like endogeic worms, but with a big difference between the black one that really burrow deep and the green one that burrow shallow. Okay. And now, if we want to validate and to use these functional groups based on bioturbation, we need to find new terms. Okay, and it's our choice, but we hope people will use it. And for example, the group on the left, we will call them intense tunneler, meaning at the same time that they will burrow a lot and big burrow system. The red group, we will call them deep burrower. It means that they burrow vertical burrows, but not that much. And it's a true meaning of a burrow. It means as soon as you got a burrows, you don't need to have 2 or 3 burrows. A burrows is enough to do what you want, that is eating at the soil surface and hiding in the soil, in depth. Okay, we can relate this group somehow to something we all know about anecic species on the left and epianecic species for the red group. Of course, the blue group, it's litter-dwelling species. Of course, we can call them or relate them to epigeic species. And for the two last group, I won't speak about the intermediate group. It's what we will call bioturbators. Bioturbators means that these worms are burrowing a lot, but they don't go to the soil surface. It means that they will cast behind them, and they will do a lot of cast below ground and a lot of refill burrows in the soil. And once again, the big difference between the green and the black groups is either they are deep or shallow. At the very beginning, we were very happy to define what we call the deep bioturbator species, and we wanted to call them the hypoendogeic species. And we were sure it was a new term. And after a really accurate reading of the Marcel Boucher book, we find this word, hypoendogeic, in the book of Marcel Boucher. And he even explained that for him, the true endogeic worms were hypoendogeics. And for example, he said that Caliginosa, Chlorotica were not real endogeic earthworms. I try to locate some species you can easily find in the UK. And for example, the deep bioturbator or hypoendogeic worms will be Aporectotherica or Orthalasion cyaneum. The shallow bioturbators, or we can call them epiendogeic, will be Chlorotica. For this classification based on functional characteristic, Chlorotica, the green morph, is not intermediate, is shallow bioturbators, or Microscolex phosphoreus. For the litter dweller species, of course, we find Lumbricus castaneus or Ezanelia tetraeda. And deep burrower, epianecic worms, are, without surprise, Lumbricus terrestris and Aporectothera longa. And perhaps what was the most surprising for me is that you don't have a lot of intense tunneler in the UK, and I only find Aporectothera nocturna in this group. This means that this functional group is perhaps rare in the UK. And as you can see, there is 6 groups, but somehow you can find again a ternary plot with the 2 groups more endogeic in the upper part, the epigeic on the downward part, and anecic on the left. Okay? And then what are the difference between Boucher ecological categories and our functional groups. It was simply tested by making ellipse for all the species that Marcel Boucher called anecic, epianecic, intermediate, endogeic, etc. Here, it's a result of the assignment of Marcel Boucher, not ours. And what you can see on the first axis, there is a quite logical separation between epigeic worms of Marcel Boucher and anecic worms of Marcel Boucher. The horizontal axis is quite clear. But as you can see here, the second axis, the vertical axis, is very messy. It means that on this axis, there is a big difference between ecological categories and our functional groups. At this stage, it's quite clear that we define groups, but we don't validate them yet. There is still work to do. And for example, we try to validate them using infiltration tests. When the worms burrow after 1 month in the soil core, you can do an infiltration test within the soil cores, and we measure the speed at which the water goes through the soil cores. Okay, it's not that impressive, but here, if you look at the results, you can see that the burrow system made by the endogeic and the epigeic species, it means the more shallow burrow system, where the soil core, where the infiltration was the lower, of course. Okay, this is not the only validation possible, but it is a first step in the process of validate these groups. Still, there is limits to our functional groups. The first one that we use only one soil types, of course, because it's already a huge work, but we could not use several different soils. Okay, and this soil is without obvious flaws. It means every worm can accept it, but nobody knows if the earthworm behavior can be modified by soil types, and this remains to be studied. We only used, as explained in my talk, physical functions, but of course, earthworms indirectly influence a lot of different functions in the soil. Let's think about biogeochemistry and nutrient release for plants, for example. And another limit of this work is that earthworms were all alone in the soil cores. It means that we know nothing about possible interaction between worms. And then what next now? We have groups, but what should we do with that? First of all, I have to say that there is a limited amount of citation of this paper, 17 citation in 1 year. It's okay, it's not exceptional. And on the paper, on the results of Marcel Boucher revisited is of course more cited because for people it's less new. It's talking about true anecic, true endogeic, and perhaps true epigeic earthworms. What was surprising is that this kind of result receive a good welcome by naturalists or citizens. For example, people ask me to translate the figure in Dutch or in French. In French, it was for Quebec, not for France. But the problem is that science, as you know, is very conservative. And if you present something new, but that's all, it's not enough. You have to prove that it's very a progress for everybody. And another remark is that this work is still on progress. 1 year ago, I've got 50 species. Now it's 60 species, and there is more to come. People from Romania, Croatia, and Austria will send worms. So we hope in a few years to have something like 100 species studied and perhaps to revisit the functional groups. And what about the future? Okay, once again, it's good to have new groups, but you have to prove that they can be used efficiently. And the first point I want to present here is that we measure somehow soil functions for every species. It means that we know in one standard soil what a worm will burrow, how much he will cast, where, how much litter he will consume. It means we can relate these characteristics to functions. Okay, the main limit here is that we know very few on possible interaction between species or between earthworms in the same species. But if you got communities, if you assume there is no big interaction between worms, you can multiply T species by abundance and you can compute amount of functions. For example, amount of burrows that should be burrowed, amount of litter that can be buried, etc., etc. This is something interesting. This is something purely theoretical for the moment, but we will try to validate that with some colleagues in the future. The other approach for the future is to use artificial intelligence, of course. And for example, you can observe in the field a lot of burrow systems. And because we have a database of burrow systems made by a lot of species, we can try to assign burrows to species. It will be very difficult, but at least to functional groups. And for example, in the picture here, you can see a very thin burrows, almost refilled, probably done by a shallow bioturbator in blue here, and a very large burrows. Okay, it's quite horizontal, and we can assume it's done by an intense tunneler. This is the true view we can have with these new functional groups. And to conclude, important message for me is these groups were not done against Marcel Boucher. And the first things to remember is that Marcel was right. Marcel was right when he was doing ecological categories, for sure. It was a wonderful work, it was a useful work. But information was lost along the year because people believe it was functional groups. They were not. Our functional groups now are made for a different purpose. Now we want to assess soil function, the role of earthworms in soils. This is a completely different main aim. And this is why, of course, ecological categories and functional groups are different, but not completely different. The anecics of Marcel Boucher are not completely different from the intense tunneler or for the burrower functional groups. And as a last word, I will say that for me, it will be very important that we find a way to translate the book of Marcel Boucher, at least in English, for the whole community, because I really think that one of the main problems was that all the very good paper or books made by Marcel Boucher were only written in French in the past. Thank you.